Okay, we talked in the last video about the first half of this chapter, which is about convergence. The second half of the chapter is about introducing the idea of power series. Power series are still infinite series, but they have x's in them, so they have a variable in their within the series. We started power series by creating them from scratch. So we said, okay, we could build a power series, and one way we can build a power series is with a Taylor or Maclaurin idea. And the Taylor or Maclaurin idea is I would like to create a series that behaves exactly like f of x at the center. So you have a center. For Taylor, it can be any center. For Maclaurin, it just means that the center is going to be at 0. At that point, our series should have the same first derivative, second derivative, third derivative, as far out as we choose to go. And at that point, the function should also have the same value as our series at x equals a. And the way you build a Taylor polynomial or a Maclaurin polynomial and then build it into a series is you take a bunch of derivatives and you evaluate those derivatives at the center. Whatever derivative you're on is going to match your factorial and your exponent. So my series is going to have, my first term will be just the value of the function at a divided by 0 factorial, which is 1, times x minus a to the 0. So it's really just going to be the value of the function. My next term will be the first derivative evaluated at a divided by 1 factorial times x minus a to the first. My next term would be the second derivative evaluated at a divided by 2 factorial. So that's how I create one myself. So this would be creating a Taylor or Maclaurin polynomial. Remember, if it's Maclaurin, that just means that you're centering at x equals 0. Okay. Then we said, okay, the other way we could create a power series is we could add on to existing. We could use our existing building blocks. Maybe that's a better way to say it because it's not always addition. So we could use our building blocks, the ones that we know, to create a new series. So one way you could do that is I could say, here's the power series for f of x. Go ahead and find the power series for 2 times f of x. Another way you could do that is you could say, we know that e to the x is 1 plus x squared over 2 factorial plus x to the third over 3 factorial. And so then I could ask you to figure out the power series for e to the 3x squared. And we could build a power series that way by using the building blocks and replacing. So if I wanted to find e to the 3x squared, that just means that I would replace all of my x's with 3x squareds. And that's easier than building it from scratch. We could build it from scratch, but just notice that if we did build it from scratch, as we're taking all of our derivatives, we would have chain rule, which then would result in product rule, which then would result in more chain rule. So this is easier because we can just use the existing series that we know and use those as building blocks. The other way that we could create a power series is we could use geometric. So the fact that we could say, well, if I start with 1 and I keep multiplying by x, then I know that a is 1 and I know that r is x, so I know that the sum of this is 1 over 1 minus x, and I also know that it converges as long as absolute value of x is less than 1. So we could use that to create a power series. The other thing we could do is we could use calculus. We can do term-by-term differentiation and integration. Oops, term-by-term. So I could say, well, I know that the derivative of this function is negative 1 minus x to the negative 2 times negative 1. So that would be 1 over 1 minus x squared. And now I can take the derivative of each term, and I can say, well, then I know that this function is equal to 0 plus 1 plus 2x plus 3x squared. And that's going to be on the exact same interval as the original. We can also do term-by-term integration. So that gives us a few more power series that we can create. All right. So our power series now are these useful series that have x's in them, and they look like polynomials. So they're easy to differentiate and integrate. What we do, our next kind of subtopic here, is that when we use a power series to approximate a function, we get an interval of convergence. It doesn't approximate, it might approximate the function for all values of x. It might approximate the function just at the center. It does for sure at the center. And it might approximate the function for some interval. There are kind of two options for interval of convergence. One option is that you have a geometric series. And if your series is geometric, then you just want to make sure that you put whatever you get for your multiplier is going to be less than 1. The absolute value of the multiplier is less than 1. So that's how you figure out the interval of convergence. You do not have to test the endpoints because with geometric, you know that the endpoints are not included. So that means that our series approximates a over 1 minus r as long as whatever is involved in r is less than 1. The other way we can get an interval of convergence, if it's not geometric, is we can start with the ratio test. The ratio test tells us a radius of convergence. And then after we get that radius of convergence, we solve for x so we can get kind of an interval of convergence. But then we test the endpoints. And when we test the endpoints to see if they're included, what we do is we go back to all of these tests that we had before, except for the ratio test, because the ratio test won't work. So when we're testing the endpoints, we wind up checking to see if our series converges by p-series or by ratio not by ratio test, by alternating series probably. So we use the endpoints to see if we should include them. And then we write the interval from there. The other big topic that comes from power series is error. So it's not practical or possible to use infinitely many terms. So instead of using infinitely many terms, we stop ourselves and use maybe 50 terms or maybe 4 terms. And there are two possibilities for the error. One possibility is that whatever number we plug in for x gives us an alternating series. If we have an alternating series, then we can use the alternating series error. So the error for using k terms at x is going to be less than our next term. And that's a really easy error, so I really hope that you have alternating series error on your AP test. But the other error option is Lagrange error. And the Lagrange error bound is, again, it's an overestimate of the error. The error, if we use a kth degree polynomial to approximate some value at x, is going to be less than or equal to the kind of the next term, but not exactly. Oh, I should have put absolute values around that. Kind of the next term, but not exactly. It's the next derivative evaluated at some value z divided by the next factorial times x minus a to the next derivative. This is just the next term almost, except that z is between x and a, so it's between what value we're evaluating at and our center, and it makes the error as big as possible. So we choose a z to make the error as big as possible. So Lagrange error says, okay, it's not alternating, so we have to use Lagrange error. We need to take another derivative. We need to divide by another factorial. We need to raise ourselves to another power. But we're not going to just plug in the center to our other derivative. We're going to choose what value makes that next derivative as big as possible. The reason we do that is because we would like to overestimate the error. We don't want to underestimate the error. All right. This is the chapter in a small tree that only took half an hour to describe. All right. Good luck. Have fun.